Hey guys, welcome back to part two of classifying chemical reactions. Today is Thursday the 26th, and we're going to continue our lecture on classifying chemical reactions. So we started out yesterday talking about synthesis reactions, decomposition reactions, and combustion reactions. I also talked about some unique ways to identify these. Um, now remember, if you have any reaction, on the left side you're going to have your reactants, and on the right side of the arrow you have what's called the products, right? The stuff you start with is the reactants, the stuff you end with is the products. In synthesis reactions, you usually start out with two or more things. So here I'll just put two things, A and B, or three, right? Two or more things, A, B, and C, and they combine together to make one product, right? A, B, C. Here I started with three things. Here on the right, it's something completely different, but they're combined together to make one product. Decomposition reactions are the exact opposite. You have one product, or you have one reactant, and they react. When they react, they separate into separate entities, more than one entity, right? They decompose, they break apart, they separate. Now with combustion reactions, these ones are also pretty simple to identify. You always have some carbon, hydrogen, oxygen chain, right? Some form of CHO, and that's going to combine with O2, which is how in chemistry we show that stuff is burning or exploding. And then it creates carbon dioxide, CO2, plus H2O, which is water. Right? And you're always going to have these three things for combustion reactions. You're going to have oxygen as a reactant, carbon dioxide and water as your products. Now for number 4, we're going to talk about single replacement reactions. And then the fifth reaction we were talking about are double replacement reactions. And I'm going to give you easy ways to look at these reactions and identify which is which, because that's what our goal is for these classifying reactions. You just be able to tell what type of reaction we have. Now, for single replacement reactions, they look like this, right? You have product A, or you have reactant A, and then you have a compound in reaction, compound BC. And what happens is the things that are similar will replace each other. So let's say A is a metal and B is a metal. Well, A is going to come in here, replace B, and bump B off, and B is going to be all by its lonesome over here. And you can see that that's exactly what happened on the product side. We have reactant A that jumped into this compound with C, so now you have your product as AC, and B just got bumped out, right? Left out in the cold. Now, some examples of this are copper. Let me change this color. All right, let's say you have some copper. You have some copper, and you put that copper into a silver nitrate solution. Well, copper and silver, those are both metals. What's going to happen is the copper is going to come here, bump out the metal, and the silver is going to be all by itself, right? And that's what you see as the product side. You see that the copper is over here combined with the nitrate, and the silver is just by itself. It got bumped off. It got replaced. And here's another example. You have these two reactants. You have zinc, solid zinc, and then you have a solution of copper sulfate. Well, what's going to happen is zinc is a metal and copper is a metal. So zinc's going to come in and bump off the metal, and then copper is going to be all left out in the cold by itself right there. And that's exactly what you see in the products, right? You have zinc combined with sulfate because it came in here and replaced the copper, and then you have copper left out in the cold. Now, an example of this is called the rusty nail. It's called the rusty nail. Um, okay. So you have iron, which is represented as the nail, right? This is your iron, the nail right here. And you have copper sulfate, which is this blue solution. You could tell this is copper sulfate because it's blue. Copper has it's copper 2 actually that has this, and it floats in solution by itself, and it has this really pretty blue color. Now, what's going to happen is he's going to put the nail into the solution, right? And I'll play the video so you can see what exactly is happening.
The iron nail into the solution.
Right? He started out with this pristine-looking iron nail, had no rust on it whatsoever, no brown
Place
stuff.
the iron nail into the solution for a few seconds, a reaction takes place. The nail soon becomes coated with...
Right? And just in a few seconds, you can see that that pristine nail now has this brown residue on it. And the question is, what happened there? How did it get rusted so quickly? And the answer is that it didn't actually rust. What actually happened is the iron replaced the copper in solution. So now in here you have some iron molecules floating around with the copper molecules, right? You started out with just purely all copper molecules, but now you introduce some copper molecules or some iron molecules in here, and the copper molecules got attached to the nail, right? And as you leave it in solution, this reaction goes on and on and on. He goes to show you that what ends up happening over time is that you no longer have a blue solution because you don't have enough copper ions floating in the solution anymore to make the pretty blue color, because all the copper ions are now onto the nail. They've now attached to the nail right here, right? These are where all the copper ions are now attached to this nail. And the silver ions, or not silver, the iron ions are now here floating in solution. And that's why the solution changed color, because there's a different element floating in the solution with the sulfate. It's iron sulfate now. It's not copper sulfate, right? What happened is the iron and the copper, those are both metals. The iron replaces the copper, and the copper gets bumped out. And you can see that evidence here in this reaction.
to form...
Now, double replacement reactions. This is when you have two ionic compounds and then the metals replace each other. Here's some examples. You have lead nitrate and potassium iodide, and the lead replaces the potassium, but then the potassium goes and replaces the lead. So the difference here is that the potassium doesn't go off by itself. It actually goes and replaces the lead. So you can see now the potassium is grouped with the nitrate right here, and then the lead is grouped with the iodine. Now I'm going to use different colors in the next example. In this example, you have sodium and you have chlorine as one reactant, and then you have silver and nitrate as another reactant. Well, both sodium and silver are metals. So what's going to happen is the sodium is going to come here and replace the silver, and then the silver is going to go over here and replace the sodium. And that's exactly what you see, right? The sodium's over here, combined with the nitrate from that used to be with the silver, and now the silver is over here combined with the chlorine that used to be with the sodium. So you can see they replaced each other. It's a double replacement reaction. And an example of this, usually this forms a solid precipitate. What a precipitate is, you don't need to know for the test, but this is what a precipitate is. Oops. You have a solid now. You started out with two aqueous solutions, which is two liquids we talked about before. This is just liquid. But you end up with a solid. So you mix two liquids together and you create a solid. That's what we call a precipitate. And then here's an example. Now I couldn't find any good reactions for it. I found this very informative video that I do want you guys watching the whole video. But all I really want to show you is the part where it talks about double replacement, which is right here.
Gas displacement. Double displacement reactions may be defined as the chemical...
Now something you notice is she calls it double displacement and I'm calling it double replacement. Really it's the same thing. Displacement means to replace, right? Or to get removed or to move, right? I'm calling it double replacement because it's more understandable, and a lot of chemists use double replacement instead of double displacement. This is the more correct way to say it, though, is displacement.
Reaction. Double displacement reactions may be defined as the chemical reactions in which one compound...
So you start out with compound A and B, C and D, and you combine them together. You react them together. And what ends up happening
each of both the reacting molecules
is that A and C are now together, and then B and D are now together, right? What ended up happening is that the A replaced the B, and the B replaced the A. And that's a double replacement reaction. Again, watch the whole video. It's useful. Here's an example of it. You can see sodium and hydrogen here. What ends up happening is the sodium replaces the hydrogen replaces the sodium, and you end up with sodium over here with the sugar instead of hydrogen. The longer, typically, honestly, the easiest way to identify these, the really long ones, those are going to be double replacement. If you ever see, there. You have these really long ones where you have a big thing and a big thing combining to make a big thing and a big thing. That's going to be a double. That's a quick and easy way to identify a double replacement reaction. And that's it. Bye, guys. Have a great day.